we wanted to step back a little bit and look at this question from a global scale, but also come from a global systems scale. And for me, I wanted to look at it within the context of general systems theory. And it's a little bit abstract, but I think it's very helpful, and it can help us explain a number of things we see going on within rangeland management and within rangeland science, and within the conflict that's kind of built up between management and science over the last couple of decades or so. I think general systems theory gives us a theoretical framework for understanding the science of ecosystem management. And it also, from the management side, gives us a theoretical framework for kind of talking about and identifying specific practices that can lead to the sequestration of carbon in soils and how that might actually work. Under the framework of general systems theory, basically there's this idea that ecosystems can be managed by manipulating positive and negative feedback processes. So there's basically two ways to move the system. The theory basically suggests that systems, ecosystems, are either changing or staying the same. Pretty simple. And that change is driven by positive feedbacks or deviation amplifying feedbacks. And that system homeostasis is maintained by negative feedbacks or deviation dampening feedbacks. These are big words, but pretty simple concepts. Negative feedback example, typical example, thermostat. Room gets hot, heat turns off. Room gets cold, heat comes back on. So you saw the slide earlier. I think Courtney put it up. We had about 400,000 years of pretty much homeostasis in global atmospheric CO2. And it was maintained by a negative feedback, this negative feedback associated with annual vegetation growth and annual vegetation senescence. And it was pretty much sitting at this central tendency of about 230 or so parts per million of CO2 for 400,000 years. That, to me, fits the model of homeostasis pretty well. This is that, if we just look at 1 year, this is the negative feedback that was holding that more or less in place, where we see the growth of northern deciduous forests taking up enormous amounts of CO2 out of the atmosphere and then losing their leaves in the fall and that CO2 ending up back in the air. And this intra-annual flux, every year this flux, holding that system more or less at a central point. Okay, this is where we are now, and Courtney put this slide up before. We seem to be moving way outside the bounds of that historical trend. And this is just looking at about 30 years of Arctic September ice, and we can see what's happening here, that the global warming that seems to be accompanying this rise in atmospheric CO2 is leading to melting of our poles, and also the thinning of the remaining ice, if you look at the 2010. The absence of that ice means that we have this black water exposed, and that is a perfect absorbing surface for solar radiation. So as the planet warms, the conditions for its warming also increase. And that, I want to put that forward because it's a perfect example of a positive feedback that I mentioned earlier. It's a deviation amplifying change in the system. So we're actually moving from a negative feedback process, maintaining atmospheric CO2, into this positive feedback process that's actually driving that change that we saw earlier. And again, Courtney put this up. This is the Keeling curve, and it's describing exactly what I just said. You see these annual squiggles, which is that northern forest doing its job, taking up that CO2 every summer. And for 400,000 years, that was enough to keep us pretty much flatlined. And it's not enough anymore because we're pumping fossil fuel carbon into the air, and we're burning landscapes, and we're mismanaging our soils, and we're fighting wars at enormous carbon cost. And so all of this is pushing that system into a series of positive feedback changes that are driving this change. If we were to stop all fossil emissions, the system is now pretty much solar-driven. We've got melting ice exposing black water. We've got peat bogs that are melting and releasing methane, which is a very potent greenhouse gas. So even without fossil fuels, this system is now in a positive feedback trajectory. If you go back to general systems theory and say, well, what can we do to reverse that curve? And it's pretty simple. We just have to initiate a deviation amplifying positive feedback that moves that curve in the opposite direction. So how do we do that? How do we initiate or stop or reverse positive feedback processes at the system level, at the global level? Well, I just want to give you an example to take this very abstract concept and bring it back home. And I missed the talk yesterday about gullies, but I understand it was a great one. But basically, as a gully starts to form, it changes the way water moves over the land, and it tends to result in the deepening and widening of the gully. And as it deepens and widens, it tends to lower the base level of the watershed. And as the base level drops, the potential energy of any water moving in that gully is increased. And so you see this further gullying resulting from that. And as the channel erodes, of course, the gully widens and it begins to deepen, and it can hold more direct, it receives more direct rainfall and can hold more water. And so you see this deviation amplifying thing is going forward, this positive feedback that's driving this change. At some point, the system settles into a new homeostasis. But at the same time, we know that we can reverse these cycles. And the great work of Bill Ziedick and Clothier from 2009, everybody here is familiar with, a book full of examples of how to actually initiate the reversal of that positive deviation degrading cycle and turn it into a positive deviation amplifying positive aggregating cycle. Water levels rise, water-loving plants move back in, we catch more sediment, the system begins to reconstruct itself. And interestingly enough, as the productivity of the hydrological system increases, well, recovering wetlands are fantastic sinks for carbon. So let's go back to that point, the results of the Marin Carbon Project, where we were able to increase our system carbon by almost 15 metric tons per hectare, year one, by applying 14 metric tons of carbon. We had this curious increase above and beyond what we had actually applied. And again, we explained that basically through increased plant growth, that because we had this increased growth, we had an increased input of plant carbon, root exudates to the soil system. We see this as a very good example of possibly the initiation of a positive feedback that's driving increases in soil carbon. Now, obviously, compost is great, but we can't put it everywhere. And the question is, how do we initiate a positive feedback process that results in improved sequestration of atmospheric soil carbon, or atmospheric CO2 as soil carbon, onto our rangelands globally? Well, obviously, livestock grazing is about half the world's land use. And the question then is, can we use livestock to initiate this positive feedback process and actually move the system in the direction we want it to go and that we need it to go?